Just going to look at a bunch of examples of linear maps between familiar vector spaces. So first off, the 0 map is a linear map from between any pair of vector spaces. And so this is the one that just maps elements by saying 0 of v is going to be equal to 0. So in other words, 0 maps the element v to the element 0. There's also always the identity for L from V to V. And so sorry, let me not get ahead of myself. So I of V is equal to V. And we have, let's see, I can take D as a linear map from the polynomials on R to the polynomials on R by D applied to P is the derivative of P, right? Differentiation is a linear operation. The derivative of a sum of functions is the sum of the derivatives, and you can always pull a scalar out of a derivative. And so now I think I'm going to write P for PR just to save time. So let's see. So I've got, I can go from P to R by mapping the polynomial P to the integral from 0 to 1 of P. So integration over the unit interval, that sends the polynomial P to a number, a real number. And it does it in a linear way because the integral of a sum is equal to the sum of the integrals, and you can also pull a scalar out of an integral. And by the same token, we can also do indefinite integration. So let's go from, now we're going from P to P. And actually, let me back up. I'm going to say Tp at x is equal to the integral from 0 to x of P. Okay, so the output of that will be a function, but it's still a linear operation. Then let's see. So if I pick a polynomial, oh, and by the way, I'm talking about these as linear transforms from polynomials to polynomials or from polynomials to R, just because that's a vector space that we talked about before. But of course, there's lots of other vector spaces of functions, maybe a little bit more complicated ones, that you could also do that for. So if we take a fixed polynomial, and then I'm going to call it T sub q. This is a linear map from P to, oops, sorry, I'm mixing notations. It's a linear map from P to P, and TQ of P is just Q times P. So it's multiplication by Q. And we can also do for a fixed C. Actually, you know what? Let's do this for F. Why not? It works for F. T sub C gives you a linear map from P to F by evaluation at C. So this is a multiplication map. This one is an evaluation map. And so as I'm writing these down, you should be thinking in your head, how is that linear? And think about like, okay, Q times a sum, is that equal to a sum of, Q times this and Q times that? And you say, yes, it is. Why? Well, there's distributivity. And, those kind of thoughts should be twinkling through your head. I don't know if twinkling is the right word there, but whatever. So what else? Let's look at some spaces of sequences. So if I take f infinity and I map it to f infinity by saying t of x1, x2, so on and so forth, is x2, x3, and so on and so forth. So this is a shift. And this is the backward shift, because everything is shifting one spot to the left. There's also the forward shift. So this takes a sequence and it bumps everybody to the right. And so people usually put a 0 in here. And then let's see what else we've got. Suppose we're looking at R3 and R2. And we're going to map x1, x2, x3 to, and then we can put like 2x1 minus x2 plus 3x3 in the first slot, and we can put 7x1 minus 5x2, how about plus 5x2 minus x3 in the second slot, something like that. So the idea here is that each of these is a linear combination of the xi's. And it's coming from R3, so there's 3 xi's to linearly combine. And then we're mapping into R2, so there's 2 output blanks, right? And so this generalizes very easily to a map from Rn to Rm. And then in this case, there's going to be like a first blank and then a second blank and then up through m blanks. And each one of these things is going to be a linear combination of x1 through xn. Yeah? And we'll see later on that this is actually going to be given by matrix multiplication. So for the example I wrote on the line just above, if we had 2 minus 1, 3, and 7, 5, minus 1, and we multiplied that against x1, x2, x3, then the output there would be exactly the things that I wrote. 2x1 minus x2 plus 3x3, 7x1 plus 5x2 minus x3, right? And then while we're here, let me just give you one other example. Suppose we go back to R3, and I'm going to look for a linear map from R3 to R. And actually, you know what? Here, let's do R2 just to make it a little easier to draw. And then I'm going to say let's take some nice set omega in R2, right? So you can think of like maybe, there we go. So there's omega. And then And so we'll call this guy T sub omega. And, oh, sorry. I made a mistake here. Let me back up. This is not R2. This is polynomials. Say, oh, heck, I just realized I would need to do polynomials in 2 dimensions. Okay, heck, here we go. It turns out, and I don't know if we talked about this before, but it turns out that the continuous functions on R2 form a vector space. If I have 2 continuous functions on R2 and I add them together, I get another continuous function on R2. We'll use that for our domain. Okay, then if I have some continuous function on R2, like maybe here's the graph of one, like this, right? Then I'm going to define T of f to be the integral of f over omega, integrated with respect to area. So that dA there, that could be dx dy, or it could be like r dr d theta, or whatever your favorite area element is. That will also give you a linear map. And this actually turns out to be a very interesting way of doing geometry. You think about sets, so omega here, you think of it as a linear map from continuous functions on a space into numbers. It turns out you can get a lot of mileage out of that perspective.